Ladies and gentlemen, this is like my sixth time starting this, so let's hope that it's a good one. I'm going to go with it, and I'm going to just cross my fingers here. This is your Unit 7 one sample T interval slash test for mu and paired data. There are actually four things that you're responsible for in this unit. A one sample T interval for mu, that's the first thing. A one sample T test for mu, that's the second thing, okay? A one sample T test for paired data, that's the third thing. And then finally, but you will not be tested on this tomorrow or Friday, but it will be on the AP test. That's why I'm including this on the video. A one sample T interval for paired data. Okay. Now, when I did these videos for you for your notes, I did the state, the plan, the do, and the conclude. I did not reteach some things, but anytime you construct an interval or you perform a test, there are some things that are fair game that I put on here just as a friendly reminder. Make sure you know where this is in your notes, or make sure you print this out so you have it out for reference for you. Since we're at home right now taking tests, they are open notes tests, at least at our school. Okay, so what's fair game? Let's talk about type 1, type 2 errors first. Type 1, type 2 errors, I didn't reteach this in this unit because we went through it in Unit 6 where I taught it, but you did see that in your homework, and again, that is fair game anytime you're testing, okay? A type 1 error is where we reject the null hypothesis and have evidence for the alternative, but we were wrong, okay? A type 2 error is where we fail to reject the alternative, have no, this should be HO, guys. I'm glad I caught that. HO, we fail to reject the null hypothesis and have no evidence for the alternative hypothesis. And we were wrong, okay? We were wrong. Make sure you discuss what consequences there are from these errors. What is power? Power is the probability of correctly rejecting the null hypothesis. One thing that's very common is says, hey, the power of the test is 0.82. What does that mean? That means there's an 82% of correctly rejecting the null hypothesis and having evidence for the alternative. Another common question is, how do we increase power? In order to increase power, we increase alpha and we increase the sample size. Probability is the probability of a type 1 error, that's equal to alpha. That's your significance level. The probability of a type 2 error is equal to beta. And the probability of power is equal to 1 minus beta. Okay, 1 minus beta. Okay, note again that there was that error there. That should be your null hypothesis. Forgive me on that. Hopefully everyone's watching this video in our class and not just looking at this cheat sheet, or you will get it wrong on the test. I'll make sure I state that in class as well. Okay, another thing, anytime you're doing a test, what's fair game on a test is asking you to interpret the p-value. You only do it when you're asked. Let's rewind and let's talk about what a p-value is. When you're performing a significance test, you guys, okay, you have an assumed truth about a population. That's your parameter. So in this case, if you look over here, our assumed truth is mu is equal to something, okay? And we put that right there in the center. Then we calculate a statistic, and that's our evidence, okay? We calculate an X bar over here. That's our evidence for an alternative truth about a population. We're saying, do we have significant evidence? Well, how we find if we have significant evidence is we have to get a t-score. This says z-score. It should be a t-score. Why is it a t-score and not a z-score? It's a t-score because we don't know the population standard deviation. We only know SX right here, the sample standard deviation. That's what's describing the sample. When we take SX over the square root of n, we then call that the standard error, okay? The standard error of that sampling distribution. Okay, so once we get this t-score, what we observe minus the mean divided by that standard error, okay? This SX divided by square root of n. We then go to our calculator, okay? And we get that p-value. So let's now go down here and look at our calculator. We go to a t-test. Now, how are we going to get that p-value? In your problem, you're either going to have statistics right here, or you're going to have data, okay? So right now what we want to do is we want to get our p-value. When we have data, that's when I give you a list of data. So I'd give you a list of everyone's scores on the math test, or I'd give you a list of how long everyone slept last night, whatever the context is, and you put that in L1. list L1, and this mu naught or mu sub 0, that's where you put what the what the null hypothesis is. Whatever you put for the center of your distribution, whatever that mu value is, you put that right here. Frequency you leave as 1, and then you go ahead and you put where your alternative is right here. So if it's a not equal, a less than, or a greater than, and then go ahead and calculate. When you calculate that, out will come a t-score, as well as it will give you your x bar, it will give you your sx, it will give you your n, and finally it will give you your p-value. That p-value then we use, right, to help us to either reject or fail to reject the null hypothesis. Now, some of you are still struggling on that. I don't have this on the cheat sheet, so write this down if you're struggling. If your p-value is less than alpha, we reject the null hypothesis, and we have evidence then for the alternative hypothesis. P-value less than alpha, reject the null hypothesis, have evidence for the alternative. If the p-value is greater than alpha, we fail to reject the null hypothesis and have no evidence for the alternative. Again, write that down, and you'll notice I do actually have it written over here for you as well. Lucky you, okay? Now, it's fair game. You could be asked to interpret a p-value. It's very common on an AP test that they ask this. Interpret the p-value. So I have here, pretend the p-value is 0.1025, okay? That means there's a 10.25% chance of calculating a statistic as extreme or more extreme than what we calculated. Not p-hat in this case. I stole this right from the Unit 6 key concepts, and you could tell I was in a hurry. I'm sorry. It would be x bar in this case, okay? So cross that off. That would be x bar. Given the null hypothesis is true. Oftentimes, a common mistake that I see, guys, is people will say, oh, the p-value is this is the probability of calculating a statistic as extreme or more extreme than what we calculated. Then they stop. It is a conditional probability. You do have to say that given the null hypothesis is true and that HO must be in context. Must be in context. Okay, let's go ahead. Let's talk about that test as long as we're talking about some things that go along with that test right now. If we look over here, when you're asked, a common question is, how do I know if I'm doing a test versus an interval? It will say construct an interval to do an interval. So a test, what am I looking for? I'm looking for the context. So in the state, that's that true being, and then fill in the blank. Use that question to help you fill in that context. The test will give it to you. They'll give you the context. Just read. Where does it say, is there evidence for blah, blah, blah? That's your context right there that you need. Your null hypothesis is always mu equals something. Your alternative is always mu is either less than something, greater than something, or not equal to. You're using keywords to help you with this. And then finally, you need your alpha level here, okay? Your conditions, random, that 10% rule, and then n must be greater than or equal to 30. That's based off that central limit theorem. Remember, for multiple choice, it may not be on the test that you're taking tomorrow, but it could be on the AP test. The independence condition, that allows us to use this standard error here. If this is met, this is what helps us use this, okay? These are connected. Okay. The normal condition, that's what allows us to get this t-score and then go ahead and get a p-value, okay? So the independence condition allows us to use this standard error formula, and the normal condition allows us to get that t-score and then go ahead and get that p-value. Now remember, the t-distribution is robust, which means if n is not greater than or equal to 30, remember we plot the data that we have. We want to check that there's no outliers. How do I check that there's no outliers? I like to check using that box plot. That right here, if you look here, I put the plots for you. How do I get there? I hit second y equals. I should have my list of data in L1 already. Okay, so in L1, that's where I hit stat edit, and I can go to that L1 and enter it. Then I hit my second y equals. I get to my plot, and I have that box plot there that shows me outliers. Then I don't have to actually calculate outliers. It will automatically show me if I have outliers. Zoom stat on that calculator, guys. Zoom stat, and that shows you that graph. Make sure you come see me in office hours if you still have questions on that, so I can show you how to do that. What am I looking for then? If my sample is not greater than or equal to 30, I want my data, if it's, I call it a medium sample in class, okay? A medium sample was, hold up, if 15 is less than n, which is less than 30. You can have some skew, but no strong skew and no outliers, okay? If n is less than or equal to 15, then you want it to be pretty symmetric and no outliers. If you're questioning, ooh, my box plot maybe looks a little skewed and you're feeling uncomfortable, that's where I said go to that probability plot. What is the probability plot? That is this, oh shoot, you can't see it right here. Let me show you on the calculator. The probability plot, second y equals, plot one on. The probability plot is this one over here, okay? Right here. That's your probability plot. Okay, with that probability plot, you want it to be straight enough, we say in AP stats, straight enough. Okay, next, let's go ahead. Sorry, there's some people in the building right now, so I'm getting a little distracted by that, but that's okay. We've checked our conditions. One thing I don't have on the plan here is you do need to say your method. So over here, the method would be a one sample t-test for mu. Now we're on to the do. This is your insurance policy, guys. This is your insurance policy. Draw your curve, put down what your mu is, your X bar, your standard error. Go ahead and run your test. That will give you all the information that you need. Fill in your t-score work. You must show your work and then tell me what the t-score value is. Write down what your p-value is and also what your degrees of freedom are, n-1. Then make a decision about your null hypothesis based on your p-value compared to alpha. State, plan, do, conclude. Let's go ahead now. Let's talk about the interval, okay? With the interval, anytime you construct an interval, ladies and gentlemen, anytime you construct an interval, it's fair game that I may ask, interpret the confidence level in blank percent of all possible samples of n equals blank. What am I going to fill in the blank here? Whatever that confidence level is. So if it's 90%, 95%, whatever it is. This method, so interpreting a confidence level is about our confidence that the method will result in an interval that captures the true, not proportion in this case, guys, the true mean. Again, my sincere apologies for going fast to get this out for you guys. The true mean. Remember, when we increase our confidence level, our variation increases as well, okay? How wide that interval gets increases. If we want a high confidence level, but not so much variation, what do we need to do? We need to increase our sample size, and then our variation will decrease, okay? Let's go ahead and let's talk about this confidence interval right now. So mu equals the true mean, blah, 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 fill in the context. I talked about the conditions. They're the same as the test. And then you go ahead in your calculator, ladies and gentlemen, you can go ahead and you can run the test. It's number 8 here, the T interval. It will look similar to the test. It just will not have the mu naught there. You won't see that. So you may have data or you might have statistics. I might give you an X bar and an SX, and you build your interval off of that those statistics, excuse me. You also will not have those alternative. It will just say, what is that confidence level? In fact, I can just go ahead and show you right now in case you're a little confused. We would go to stat, we would go over to test, we'd go to T interval. Again, if you had statistics, you would type in your X bar, your SX, your sample size, and your confidence level. You can go ahead and you can calculate, okay? We have our interval. Now, what am I looking for on the test as well as what are the AP readers looking for? I do want my lower bound and my upper bound, of course, but I also want this formula filled in. I need my X bar filled in, plus or minus my T star, times my standard error filled in my Sx divided by the square root of n and my degrees of freedom. Now let's talk about how do I find that T star. Here are my T stars in here, okay? If I go to my formula sheet, I want to look at, hey, what is my confidence level? Okay, what is my confidence level? If my degrees of freedom are 25, my T star is one of these values. If it's a 95% confidence level, my T star is 2.060. If it's a 99% confidence level, my T star is 2.787. Okay. Remember, if your degrees of freedom are not on this chart, for example, if your sample size is 40, your degrees of freedom are 39. You need to round down then to find your T star. So you would go to 30 and you'd get your T star there. I'm going to repeat that. If your degrees of freedom is not on the chart, for example, let's say my sample size is 90. 90 minus 1 is 89. 89 is not on my degrees of freedom. I round down then to 80 to get that T star. The T star then for 95% is 1.99. I then would go ahead and I would plug that in. Oopsie, guys, forgive me. It's going to take me just a second. I'm going to pause to get there. So when I'm looking at this, right, if I have to round down, I find that T star, right? I talked about rounding to 80 or whatever the value was. Then I have to actually go ahead and I have to calculate this by hand, okay? So I have to take my X bar plus my margin of error to get that upper bound and my X bar minus my margin of error to get that lower bound, okay? Let me know if you have any questions. You can always come see me in office hours or email me as well. Once you have your lower bound and your upper bound in this do part, you say I'm whatever percent confident that the interval from the lower bound to the upper bound contains the true mean, blah, blah, blah. Okay, true mean, blah, blah, blah. Okay, guys. Now what we're going to do is we're going to talk about the paired data, okay? In the paired data for the test versus the interval, I'm going to just address them at the same time. Paired data oftentimes happens when we have matched pairs experiments, okay? A matched pairs experiment, but not always. It's not limited to that. We can use a paired data test or interval when we have an observational study, such as I'm looking at the difference between a pre-test and a post-test, okay? That's an observational study. So really paying attention to what's happening in the problem. And I'll talk about what are some keywords to look at that in a second. But let's get started. With a test, what am I looking for? I'm looking for mu is equal to the true mean difference, dot, 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 and then talk about the context. The null hypothesis is always mu is equal to 0. Then the alternative is you have to decide, is it going to be greater than or less than based on the problem? Now, the easiest way to think about this, you guys, is you have to say, okay, I had to subtract. I'm looking for the difference. So if the difference is A minus B, okay, I assume that that null hypothesis is equal to 0, meaning that the difference is the same. A and B are the same. But the alternative hypothesis now, how do I know if it should be greater than, less than, or not equals to? Well, the easiest truly is a not equal to, because they will look and they will say something, do we have a significant difference? You'll see that word. Is there a significant difference? That's a not equals to. A greater than versus a less than. You want to pay attention to the word choice. What are they looking for? Are they looking for A values to be bigger? If they're looking for A values to be bigger than B values, right? They're looking for a positive difference then, because big minus small will give you a positive number. That's a greater than. But if you set it up A minus B, that's how the difference is, and we're looking for B values to be bigger than A, well, small minus big, then if we want this to be bigger than A, we're going to get negative values. That's right there. So paying attention to that word choice, how you set up the distribution. Did you do A minus B? Did you do B minus A? And what is that question asking? Okay, let's keep going here. Next, okay, alternative hypothesis we talked about, and then alpha. In an interval, you only have to talk about the true mean difference. Now the conditions change just a little bit. You do need to state in the plan that it's paired data. Now here's where you want to kind of look and see what is the word choice, what's happening, what's the context. Did they pull out a random sample? Is it an observational study or is it a random treatment? That's an experiment, okay? Is it an observational study or is it an experiment? If it's an experiment where the treatment was randomly imposed, okay, or randomly given, I'm sorry, then all you have to say for the independent condition is responses are independent. If it's just a random sample of 15 people and we're looking at their post-test scores minus their pre-test scores, well, then we still don't need to do that 10% condition. That 10n is less than capital N. And then as well as saying responses are independent of each other, okay? What I got in my pre-test and my post-test is independent of what, Cheryl got on her pre-test and her post-test. And then that normal condition stays the same. N must be greater than or equal to 30. If not, you check for skewness, outliers, so on and so forth. I've already addressed that, the same as over here. Take a minute to reflect on the conditions, making sure that you understand what I just said, writing down any questions that you might have for me. Now the do, really nothing changes in the do unless you are given data, okay? If you are given data, you'll have an L1, an L2, and you may have to find the L3. So when you go through on your test and you do a t-test or a t-interval, okay, a t-test, you're going to change that list to L3. You're not going to check the conditions on L1 or L2. You only care about the differences, okay? You only care about the differences, that L3 column, if you're given data. When you graph to check for skewness or symmetry and no outliers, again, I only care about L3. That's a common question. People think they need to check L1 and L2 for normality. You don't. It's just L3, that difference. All right, moving on. You go through, you run your test, or you run your t-test, or you run your t-interval on that L3 or on that statistics that they give you. You find your t-score just like you do over here. Now, if you notice, I have a little purple D here just to signify that that's the mean of the difference, okay? The mean of the difference. You find that p-value again with your degrees of freedom, and you go ahead again and conclude. You're either percent confident or you are rejecting or failing to reject that null hypothesis. Okay, I've really summed up everything. I believe I forgot to put that method in here for plan 2. Make a note to yourself that you do need that method as well in that plan. And then again, just my apologies. I'll say it again. Sorry for the couple errors, but hopefully you're watching the whole video so you know what the errors are in here and you just didn't, print this out for nothing. Okay. I do want to quickly, briefly talk about this formula sheet. If you look over here, let me make this a little bigger for you guys. I should have done that from the beginning, huh? I'm not starting over now. Like I said, I started this over way too many times. One type of multiple choice question that you may have that we practiced often in the last couple of days is how do I figure out what the p-value is on this table? So it's going to be extremely rare to have a degrees of freedom of 2, but let's just pretend that you had a degrees of freedom of 2, okay? And you went ahead and you have a t-score that you calculated without the calculator. So oftentimes it's a multiple choice. They give you the t-score. They say the degrees of freedom are 2, okay? Let's say that your t-score is 5.7. You go to degrees of freedom of 2. 5.7 is in between 4.849 and 6.965. Now, if you're watching and you're like, what the heck are you doing, Opal? I'm saying on a multiple choice question, they could give you a t-score, they could give you degrees of freedom, and then they'll ask you, are you going to reject or fail to reject? Or they may ask you, do you have significant evidence? Is the t, or another one, is the t statistic a significant statistic? They might say something about significant evidence. Significant evidence means we have our p-value is less than alpha, and we're going to reject the null hypothesis. So if we reject the null hypothesis, we need our p-value to be less than alpha. Well, if they don't only give you a t-score in degrees of freedom, you have to use the table to decide that. Again, if you only are given a t-score in degrees of freedom, and you have to decide if you have significant evidence, meaning rejecting the null hypothesis, you need to find the p-value using the table. Degrees of freedom of 2. If your t-score is in between 4.849 and 6.965, right in between these two values, you scroll up, you know then our p-value is in between 0.01 and 0.02, okay? In between 0.01 and 0.02. Let's practice again. Let's say our t-score is 2. Degrees of freedom are 2. I go to this row. I see 2 is in between 1.886 and 2.920. Again, you will be given that the t-score is equal to 2. The degrees of freedom are 2. I know 2 is in between 1.886 and 2.920. Since t is in between these two values, I scroll up. My p-value then is between 0.05 and 0.10. So now because my p-value is between 0.05 and 0.10, that is greater than 0.05, and I would fail to reject the null hypothesis. Again, we've practiced this in class, so go back and watch those videos if you need. This is just meant to review with you, okay? So go back and watch those other videos of mine where I teach it from the beginning. Another friendly reminder, if the t-score is negative, you take the absolute value of it. And finally, if your alternative value, okay, or your alternative hypothesis, excuse me, so your HA, if that's a not equals to, wherever that p-value is, so let's play it again. Let's say our degrees of freedom are 2 and our t-score is 8.7, okay? Degrees of freedom are 2, t-score is 8.7. That's in between 6.965 and 9.925. I scroll up. My p-value is between 0.005 and 0.01. But if my alternative hypothesis and my HA is a not equal to, I need to multiply both these values by 2. Again, I multiply both these values by 2, which would mean my p-value multiplied by 2 would be between 0.01 and 0.02. Okay, and that's only when it's a not equals to. Okay, lastly, if we look at this chart here, sometimes, you know, they'll maybe give you an interval and they'll ask you, do you have significant evidence? Meaning, would you reject or fail to reject the null hypothesis? If your blank percent interval contains not P, but mu, okay? So let's write that in. We're gonna cross that off and we're gonna put mu. I'll do it over here so I'm not confusing too many of you. So keeping in mind, guys, if your blank percent confidence interval so whatever mu equals, okay, and this is from your null hypothesis, we fail to reject the null hypothesis and have no evidence for the alternative, okay? If your blank percent confidence interval does not contain whatever mu equals, that again, that comes from the null hypothesis, we reject the null hypothesis and have evidence for the HA, okay? And have evidence for the HA. If it's a 95% confidence interval, the alpha then would be 5%. If it's a 99% confidence interval, your alpha would be 1%. Another thing about this only works if the alternative hypothesis in AP Stats is not equal to. It only works for an alternative hypothesis of not equal to, okay? Any other questions that you might have? The video got a little long and I tried this one too many times. But again, this should give you all the information that you need Like I said, there's a couple things on here where I just went fast trying to get this out to you. There's a lot going on right now as we're preparing to come back to in-person teaching. So hopefully you listened to the whole video so you got, what should change. Okay, a lot of these other things are for when I taught proportions. Any other questions? Let me know and have a wonderful night, you guys. Thank you.